This question is titled, How do I encode workflows? Why do I bother with shell in the first place? Well, I bother with shell because oftentimes I need to encode a workflow. What does that mean? Well, I'm a data scientist. I am a natural scientist. I am somebody who isn't a programmer, maybe even doesn't want to be a programmer, but wants to use programming and programming tools in order to get my work done better. And so programming for me is likely just a consequence of needing to do something at a larger scale, a consequence of needing to do some work faster, some need for automation, but it's not my reason for being. And if I think about it, oftentimes what happens is somebody gives me a command line program. Run this program, it'll submit a job to the machine learning, training and testing and back testing server. And I look at that command and I say, well, there's a little flag here. Let's try what happens without that flag. Oh, let's put that flag back on. Okay, that's interesting. Oh, if I can pass one name of a job, maybe I can pass two names of a job. And I play with that a little bit. And as I play with that, I say, you know what? Rather than having me sitting here typing commands all day long, which just seems like a good way to get carpal tunnel syndrome, I'm going to write a little bit of shell scripting in order to automate this. Instead of me saying run job 1, 2, 3, 4, 5, download dataset 1, 2, 3, 4, 5, take the results and post-process them 1, 2, 3, 4, 5, and write a script that just loops over that. But there's three parts to this, right? I have to pull in the data, launch the job, and then post-process it. This is a workflow. There is a collection of steps that I need to follow, and at each step along the way, something might happen that might affect the next step. It might fail, it might succeed, it might stall, and I need to encode that in some fashion. And this is largely one of the main reasons why you might end up using the shell. You need to take a bunch of connected tasks with dependencies and encode them in some fashion. And so let's think about how we might do that. And in fact, this is probably one of the major uses for a data scientist or a natural science type for Make. You might have seen Make or GNU Make or any of the related tools back when you were working with C and C++. I don't know if that's really realistic for all of us, but back in the days where somebody said, oh, you should learn C++ or you should learn C, and you're like, oh, I don't know about that. I gotta learn this Make thing first, but it's something that comes up quite a bit when you're dealing with building software, especially where that software is written in C or some of these languages that have been around for a very long time. And here is a very simple Make file. It specifies a target given some prerequisites. The file a.c must exist in order to generate a file called a.out, and there is a recipe, GCC, taking that input file and generating the output file. And here is my a.c, and it's a very simple little C program. All it does is print hello world, and I'm going to write Make at my command line, and it's going to build this software. I'm going to run it, and you can see my program works. When you look at the design of Make, it is actually a surprisingly useful tool for encoding workflows, but fundamentally, its genesis was as a tool for building software, specifically software in the C programming mindset, not even the C++ programming mindset, because a lot of C++ software has moved on to even more sophisticated tools than Make. As a consequence, when you look at what Make offers you, you'll often see that it is very much orientated around the thought that, okay, what would make a C programmer's life easier if they wanted to build larger C projects? And so, for example, Make has some degree of programmatic behavior. Instead of specifying exactly a.out and a.c as the inputs and the outputs, you can say with a pattern rule, oh, there's %.out, so anything with that. And it relies on a file called %.c. And so if I'm generating a.out, I need b.c. If I'm generating b.out, I need b.c, and so forth and so on. And the rule is the same for all of them. It's GCC using a special variable to indicate the prerequisites and a special variable to indicate the target name. Here's a pattern rule, and it gets templated, and there you go. And so instead of having to hard code that I'm generating prog.out from prog.c, basically the same thing as my a.out and a.c from before, I can change these names without changing my Make file. Or I could have multiple files, a prog1 and a prog2, and I can generate both of them using the same Make file, and I don't have to write them. I don't have to write this out manually. So I guess that's kind of useful, especially if you're a C programmer, but how might I use that in order to encode a workflow? Well, if you think about what Make really is, you can think about how it might be helpful for tasks that are not about building C++ C programs. For example, maybe as part of my workflow, I have to do a little bit of web scraping or I have to download something. So maybe I'll make a target called whatever.zip. And it's just some zip file that I pull from some HTTP endpoint. So in order to generate that, my recipe is do a wget or a curl operation. And to get the entire data set, I'll say, oh, its prerequisite is a.zip, b.zip, and c.zip. So when I try and make data, what'll happen is it will go and download all three of those files. Well, that'll only work if my HTTP server is running. There you go, my HTTP server is running, and you can see it goes and it downloads all three files. Fantastic. But the problem with make arises when you say, the data files have changed on the website, let me do a make data again. If I do this for the first time, yeah, it'll go and it'll grab the a, b, and c.zip as long as they all exist, but something weird is happening here. It's only doing one of these, and if I do make a.zip, b.zip, and c.zip, and then I do my make data, it says nothing to be done for data. Well, here's the thing. Deep down in make, there are fundamental assumptions that result from its use as a tool for building C software that make it a seductive tool for you to use for workflows, but you will hit a brick wall. And in the simplest use cases, make is great, but you'll see that there's just some insurmountable problems for anything slightly more complex. Now, you may have heard of workflow systems, these very sophisticated tools. Apache has a couple of different workflow tools for designing large workflows, Airflow and this and that. Sometimes they're just way too complicated, and you look at make and you see how simple make is, and you say, that's for me. But it's important to understand how far you can take it. Well, let's think about what make is really. It is a file that is picked up automatically by a command called make, that's located in a directory where you do something, that specifies targets against prerequisites with a rule for that target. The targets are files on disk, the prerequisites are files on disk, and the rule is something that gets passed to some program, typically some little shell command. And this tells us one immediate reason why people like make. Instead of some very complex workflow system where the command that you type at the console can't just be cut and paste into the workflow system. In make, what you would do with a typical make file is you just write the rule. You'd say, oh, gcc-o, blah, 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 -i, blah, 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 and all of these flags. Does it work manually? Sure. Paste it into my make file, and you're off to the races. And this is one reason why people like it, because it's so simple. Well, what you can think is when you build these prerequisites, what make is doing is generating a graph for you. And it's starting from the target and determining the dependencies down this graph. And it's building a control flow graph for you. It's saying, in order to build target, I need to build this prerequisite, which requires that I build this prerequisite, which requires I build this prerequisite. And it's a control flow graph because implicitly, each step along the way, there is another branch of what happens if it fails. And this is just this thing exits. It exits with an error. So what you can think is here is a control flow graph from top to bottom. Build the first prerequisite. If it fails, exit. If it succeeds, build the second prerequisite. If it fails, exits. Build the third prerequisite. If it fails, exits. And make figures out the order in which to build these. It says, oh, this prerequisite depends on this, so it figures out the topological ordering of these, the topological sorting of these to make sure that everything that's needed to do the next step is available. And it doesn't have to be just this linear section of prerequisites. It could be a tree where you have to build 50 things at this level, which then build 20 things at this level, which build 3 things at this level, which build 1 thing at this level. And make can automatically parallelize these. So it can say at this level where you're building 50 things in parallel, that don't depend on each other, you could build them in parallel. But fundamentally, the control flow graph is very simplistic. It is really just build. If it succeeds, keep going. If it fails, don't keep going. And the ability to do this in parallel. And you can't really specify other actions. And critically, the marker for whether something succeeds or fails from the perspective of a make file is, did it generate a file with this name, with this timestamp on disk? Which means any sort of workflow which has a criteria of this thing needs to be rerun, but you can't check that by just looking at the presence of a file on disk or the timestamp of a file on disk, is very difficult, if not unnecessarily problematic to encode in make. Now, make does not require that you write shell scripts. In fact, you can have very complex targets in make files that themselves are in any arbitrary programming language. So here, this is supposed to create a target on disk called target, and it does it by encoding a Python script that doesn't actually generate any data. But I'm going to mark this as a phony target to say, oh, this thing doesn't actually create a file on disk. And every time I try and make this thing, it'll just rerun it from scratch. So you can sort of escape this assumption of, does a file exist on disk by marking something as phony? But think about this. What if you needed to have a workflow that created an SSHFS mount to a shared location where you have some data? Well, can that be thought of in terms of something existing on disk? I guess it can be, because you can see if the SSHF mount has some file in it. Okay, what if you needed to wget something? Can you determine if that's newer or older, if that's up to date by looking at a file on disk? No, you can't, because you need to actually do the request, and you have to look at the cache fields, and you have to look at the last updated fields in the headers. So you can't really do that. What if you needed to check if, for example, some system level operation was tweaked correctly, like some sysctl was tweaked correctly, so you can launch a Docker container and do something else? Can you check that with the file on disk? No, you can't. But if you have to check if a Docker container has already been launched, can you check that with the file on disk? No, you can't. And anything which cannot be easily encoded in a file on disk, the only real escape hatch you have is you say, oh, just always rerun this. But otherwise, it becomes very problematic. Here's why you probably would use make in the first place. It's more or less installed everywhere. And so it is fairly unlikely, outside of maybe within a really cut down Docker container, that you would find an environment where make doesn't exist. It is a relatively simplistic grammar. There's really not a whole lot to it. It is target, prerequisite, recipe with some patterns on the target, and a couple of things like the ordered versus the unordered prerequisites. But beyond that, the simplest make file is probably shorter than the simplest workflow in any other tool that you use. The tooling for it is generally pretty decent. You can tab complete. You can say make, I forgot the name of it, tab, tab, tab. Oh, it tab completes for me. And for the most part, because make is so static, it can actually do this tab completion fairly well. And it's very constrained, so there tends to be less boilerplate than, say, a shell script, like an ad hoc shell script that you write, with a very consistent grammar. And it's very suitable for, let me try this manually. Does it work? Paste into my make file and go on with my life. But the reason why you would avoid make is, one, it is incredibly primitive in how it deals with strings, specifically with file names. We've talked previously about what you would do if you have a space in your file name. Do you know what you do in make if you have a space with your file name? You don't use make. Its ability to handle anything outside of how files used to look when make was first created however many years ago is quite limited, and you're going to have a really bad time. Its ability to do quoting and whatnot is very limited. And so generally, that is a hard stop for using make for anything. Anytime you need a complex string handling for like a file name, make's not necessarily going to get you where you need to go. It is minimally programmatic, which means oftentimes you don't want to hard code all the targets and all the prerequisites. You want some sort of template or some sort of pattern. So you have pattern rules and make, okay, that's fine. But what if you want to say, create one target for every file that exists in this directory by looking at what's in that directory? Can you programmatically at runtime generate a graph definition? No. And because it doesn't expose the graph that you can manipulate it, what you see around make is there tends to be these layers of tooling on top of it, like AutoConf and AutoTool, that stack on top of make in order to run something that creates a make file, because the make file itself isn't sufficiently programmatic to be able to say, oh, look around, let's see what I have in my environment. Look around, let's see what files I have. Construct targets based off of that, and then expose that as a graph that then could be further manipulated, and then I can run against. Its orientation around the presence of files works if your marker for did something get run and succeed is based on the presence of files. But unfortunately, there's not really any real control flow. You can't say, download this data source, and if the download fails, do this specific action. All you can do is say, if the download fails, bail out and die. And there is no data flow. You can't say, have this rule perform some operation which passes data to this other rule. As a consequence, what you'll find is you can't pass parameters to a make file even. You can't say, oh, run make, and then here's like -- prod, and just do the prod version of this, or the dev version. You have to encode that in the names of the rules. And so as a consequence, make is just very limited outside of incredibly simplistic workflows that are more or less tiny little shell scripts or shell snippets that you want to order in some fashion. But there are other options. Somewhere between writing a completely custom shell script and writing a make file is a middle ground where you can write really simple shell scripts. And I want to open up your thought process, especially those of you who've used make before, to how easy it is to take the core mechanics of make and just encode them in a shell script. Here is a shell script. And what it does is it specifies some dependencies within itself in the form of a case statement. And it says, if you want to build D, then you're going to run the function ABC. Or the run the function depends with A, B, and C. If you want to build A, B, and C, you're going to see if this arbitrary predicate, which happens to be does the file exist, and if that arbitrary predicate fails, then you're going to create that file by using the touch command. This depends re-invokes the same script with the names of the arguments. So this is a shell script that recursively reinvokes itself as you go, which allows you to then specify a very simple graph of this depends on this, depends on this, depends on this, with arbitrary predicates that are no longer dependent on does this file exist, because this could be anything. This could be any command that gives you some exit code. And you can see, if I have a very simple make file like that, you can see a process D, which then triggered the processing of A, B, and C, and you can see exactly what it did. It actually created A, B, C, and D on disk for me. We can do even more sophisticated things with a shell script without writing that much code. We could say that the general make approach is really more or less the same as encoding some control flow in the form of functions and a call graph. So another way that I could replace make is I could write shell functions, and I could encode their graph just using shell operations and short-circuiting. I could say run node 1, A, and if that succeeds, run node B, and if that succeeds, run node C, and if that succeeds, run node D. And you could think that's basically the same thing as the simple make file, and it's basically the same thing as my previous shell script. And each one of these nodes is programmatically just a shell function. So it turns out that there's some ways that we can write really simple shell scripts that replace the use of make for workflows, and these are only a couple of lines long, and this may be a more adequate tool, especially if we run into those hard limitations that we run into when we use make. But with that said, you have a lot of options for encoding workflows and some extraordinarily sophisticated and complicated tools. Is it really worth your time to learn those tools? Well, I don't know. It depends on how complex your workflow is. Is it really worth your time if you've got 5 minutes to put something quick together to save you 3 minutes the next 10 times you do this? Maybe, maybe not. And in that case, maybe reaching for make if you're willing to stay within the hard guide rails of make, or write a shell script, one of these two approaches, and think a little bit beyond make, but still can keep your life a little bit simple. But these are your options for trying to encode workflows, and the mindset behind why you might do this and how you might do this at the command line.